Hey everyone, and welcome to the next session in the YYC DataCon today. So I'm going to be your host. For those of you who haven't met me yet, my name is Ben Reeves. I'm one of the co-organizers of the DataCon, and joining me today, I have Chris Chalcraft, who is a solutions architect with Databricks, and we've been connecting a little bit about the ways that Databricks can, and some of the stuff that he's going to be talking about is going to be useful even in my work personally. So I'm, quite looking forward to this session, and I'm sure that there'll be a lot of great data engineering and, scalable questions that'll be addressed in here. So kind of without further ado, I'm going to turn it over to Chris. Thanks so much for joining us.
Hello all. Okay, let me just get a share up here. Okay, let me know if you can see it okay. Yeah. Thanks for the intro, Ben. My name is Chris Chalcraft. I'm at Databricks. Currently been there for about 4 months. But previously was within the energy industry in geophysics. Did some data science at Chevron. And so today I just want to go through Delta, maybe like what is it, how many people have actually heard of it, and kind of how it can make your data lakes more reliable and more scalable. So we'll leave questions to the end. Okay, yeah, and so a word on Databricks. Like they really promote this, like the lake house aspect, right, where you're trying to build, data warehouse functionality on top of your data lake. And so really Delta is the underlying technology that kind of helps enable that. A real great thing about the company is that they have like a real nice commitment to open source. So it's built on Apache Spark, and then Delta itself, it is just a storage file format. So it is open source as well, and that's kind of going to be the underlying technology that we're going to talk about to kind of like build that reliability into your data lake. So if you're interested in checking out more on the open source Delta project, you can go to delta.io and you can check it out. Okay, so let's move on to kind of like the promise of the data lake. I know there's been a lot of talk around kind of making sure that data is accessible to everybody, and there's always one single source of truth. Whether that is kind of feasible, from a practical perspective, it's still to be seen. But let's talk about the promise of the data lake and how you can just dump all your data there rather than worry about having some kind of schema on write, right? And so it allows you to kind of forego that process and deal with it later. So, businesses nowadays, they're trying to collect so much different types of data. That could be a mix between, your structured, unstructured, structured, unstructured, and semi-structured type data. Once your data is collected, you want to be able to build, at the end of the day, kind of like data science, machine learning type analytic workflows, and start making those data-driven decisions in your company, and hopefully, get a certain amount of realized value associated with it. But the problem is that, without some kind of structure and reliability checks, you end up ingesting, a lot of garbage from time to time. Or in the worst case scenario, you'll store that data and, it'll propagate into your models that you're trying to glean insights from, right? As well as different BI and analytics workloads. And in order to go back and try to fix those data sources, you'll read it, fall into different types of problems later, right? When you're trying to fix data sets, but somebody now no longer has access to it because it's under maintenance or something. And so, I mean, I know the people in this talk, or in this conference, they're pretty data savvy people. And, you always get those people within the business function kind of saying, well, like we have all the data, right? So why is my data science model taking so long? Right. And, in the meantime, you have this kind of like the poor data scientist, locked away in his broom closet of an office, trying to stitch together, all these disparate data sources, that they've collected from people all around the company, and so we want to try to avoid that kind of stuff. So let's talk about what a typical data lake project will look like. I mean, this is just going to be just like an example that kind of highlights some of the different problems of working in this kind of distributed object storage. So for this scenario, we're going to look at having a streaming event, right? And you want to be able to do both your streaming analytics as well as your AI and reporting, right? So what are we going to have to do here? Well, we can. Spark has a structured streaming API, right? And so you can relatively easily build a streaming analytics workflow, right? But there's no guarantee on the quality of that data set, without having some kind of historical and reliability checks. So in order to do the historical AI and reporting workflows, you have to also set up a cold stream, right? So you're dealing with this Lambda architecture style, right, where you have this kind of hot and cold. The hot to do the real-time analysis with the less, no guarantee on accuracy, but pretty good. And then the cold stream, which is slower and will give you more curated look at the batches. So that's relatively easy to set up. You can set up a Spark job as well to store those historical queries, and then in the end, kind of like do your AI and reporting. So the challenge with this, is that your data is messy, right? I mean, that's just like that's just being real, right? Like, everybody has to deal with messy data. And, you might have things where people are changing the schema upstream, or, some kind of corrupted data. And so you need to write in kind of these validation checks to kind of match your both your streaming workflow as well as your historical workflow. So that's not too bad, but I mean, it requires it requires you to understand your data set and make sure that you have those checks in place. So the challenge 3 is that you have, so you might get bugs, you might get crashes on specific spot instances. And so in order to make sure that you're flexible enough to fix these types of problems, you need to break up the data set into different partitions, right? At a certain, maybe like a time granularity. So you can build, these custom scripts to do the reprocessing, right? So you don't have to actually load all of your data, load all your data in order to make some kind of fix. So this is what I said here. So partition your data, so you can kind of go back and do that reprocessing. And so now the challenge 4 is around kind of like the updates and deletes. So it is relatively easy to append data, right? You don't have a lot of conflicts or problems, but changing data can be tricky. So instead of doing, so what people will do, depending on like the size of the table, right? You would just copy the entire table, maybe like once a month, make certain changes, and hopefully nobody's reading the data at that time, so you have to deal with the scheduling. so you have to schedule to avoid conflicts. And so, so this can be a little tricky and annoying to handle. But I mean, it is possible. You can just schedule certain maintenance times for data sets. But this can be costly, both time and money, or angry engineers banging at your door. So what's the common theme that we're seeing here is that we're spending a lot of time solving these system-related problems rather than extracting the insights from your data set. And so, we want the end user, the person who's delivering the data products or the analytics results. We want them to be focusing on the data set, right? Versus trying to handle all these types of system problems or issues with performance issues on your data set. Especially coming from from that kind of like data science background, you're often not evaluated based on how clean the data set is, or whether you have some kind of efficient reprocessing job that makes it available. So really, you want to be focused on the end result, the model deployments, and the business metrics. So the data lake distractions are kind of some of the things that I highlighted here, like the no atomicity. That's was when when you're dealing with like file-based data lakes, like distributed object stores. If you get a failed production job, you can leave the data in this kind of corrupt state, and you're going to have to deal with this kind of tedious recovery process, maybe leveraging some of those tricks that we seen before. There's kind of no quality enforcement, right? Because it turns into a dumping ground for data, and it kind of creates this inconsistent, unusable data. Especially, it's difficult for people to be like onboarded and handle like that data discovery, right? Nobody can just like go in and look at a big big partition and find and just kind of figure out what data exists. And then there's no consistency in isolation, making it difficult to mix data sets and deal with that kind of like scheduled updating time, right? So at the end of the day, like all these distractions are preventing you from doing your job, and you might have some curmudgeon within the company, saying, well, why has, management decided to use this data lake when it's just causing all these system problems, right? And they're saying, well, it's better for me to just process the data on my own machine, depending on the size, or, I'd rather just have my data in a database somewhere. Yeah. Okay. So I'm kind of like losing track of my slides here, but like, so this is the same thing. Like, you want to get the insights from your data set. You don't want to deal with the systems problems, right? And I mean, this is not new to anyone. Everybody knows that the data is messy, and there have been many improvements to like improve our way of working. Whether it be like different BI tools, agile mindsets, DevOps stuff. But at the end of the day, the data is still messy, and it's causing a huge blocker for people to deliver these data-driven insights. Okay, so let's talk about delta lakes. I mean, this is a term that I kind of found confusing when I first heard it. But I mean, at the end of the day, it's just a data lake, but it's leveraging the Delta format to help provide some kind of reliability, to fix some of these problems that we've mentioned, and also improve some performance, to handle, because around different, I'll get to it later, but you can deal with different performance improvements. So it's a standard for building data lakes. There are different formats available as well. Like, there's Iceberg and there's Hoodie as well, right? But Delta is one that Databricks definitely promotes, and it's really good. It's open source. It's based on the columnar Parquet format, right? So it has all those compression optimizations built into it, as well as the ability to filter by columns, right, rather than row-based structures. But the idea around it is that it gives you a transaction log alongside your data set that contains different commits and metadata associated with your data set. So we can do some fancier things with the performance and reliability. And then the last thing I'll mention here is that, it's compatible with the Spark API. And because it's open source, many people can build integrations on top of it for kind of native tools. So adding reliability and performance, so you can kind of streamline that approach to get that data science and ML workflow. And this is kind of what I was mentioning here. So Delta will support your batch, your streaming, different kind of data manipulation techniques. But at the end of the day, it's relatively simple, right? It's just Parquet files, under the hood, and the associated transaction log that will give you that kind of reliability. And so some of the key features that I'll mention here is the ACID transactions to make sure that your data is, not corrupted, or you're loading some partial data sets. There's schema enforcement, so you can get that kind of data warehouse reliability by kind of enforcing a specific schema, but then also giving you a flexibility to allow schema evolution as well. So it's just a flag that you can turn on and off. It creates this kind of like unified batch and streaming. And then because it has the transactional log associated with it, you get this capability of time travel and creating the data snapshots. And this is one thing that kind of people talk about, and there's sometimes like a little misconception around the time travel where people think it's kind of like data version control. To some extent it is, but it's not really intended for long-term, data versioning. It's mainly just so you can kind of fix these types of problems that we indicated, right? Where I think the default is to keep like 30 days worth of your data versioning. And so you can kind of go back and you can fix those problems if something does arise. Okay, and then so now for the performance aspect. So now that you have this like reliable data set and you're kind of getting your data ingested in a kind of with less friction, right? A little bit more streamlined. So now we can take advantage of these different performance capabilities. And so some of the key features that I'll mention here, you can add the indexing, you can deal with different compaction, right? So if you have too many files, because you have this metadata that is alongside your data set, you can do things like data skipping or caching for, only loading different incremental parts of the data set. Yeah, and then finally, like there are connectors all over the place. So regardless of the tool of choice you're using, most likely there's a connector available. And so it kind of the open source aspect of it is like kind of it really encourages like growth and adoption, and it makes sure that you don't have this like vendor lock-in, because at the end of the day it's just open source Parquet under the hood. So if you can remove your Delta log, you're left with just the raw Parquet files at the end. So let's take a look at the previous scenario. So just to remind everybody, this was kind of the scenario that we were looking at for the challenge. And we're going to see kind of how Delta is going to address some of these issues. So when we talk about a Delta Lake architecture, I mean, realistically, it's just this kind of incremental refinement of data from going left to right, right? And so the left, you kind of have your raw data sources, different types of CSV, Parquet, whatever kind of files, or you might have like different event streams. And you want to land that data in the data lake and then take advantage of that cheap storage. And then, not have to rely on data systems that might be expensive to store it, right? Or that maybe are having issues scaling, right? You're constantly having to increase your limits of your databases month after month. So this architecture is trying to remove all that and just deal with that kind of incremental improvement. And so the hallmarks of this architecture is that it gives you the ACID transactions and you can focus on the data flow rather than the failures and systems problems. And so like you're guaranteed these kind of consistent snapshots. So once the data is written out, it's not going to be lost and it will not allow writes of partial data. Okay, open source, I kind of mentioned this before. Yeah. And then with respect to the scaling, it's like, it's powered by Spark, so you get the access to it's compatible rather with the Spark API. So you can have access to that unified streaming and batch type workflow. And it's relatively easy to convert your existing Spark jobs with minimal modifications. And I'll kind of show you that later. I guess just a quick note on the, like this multi-hop medallion architecture, just to kind of create like a little bit of a baseline. But, you might have different containers set up for like raw, some kind of filtered, augmented data set, and your gold level business aggregates, right? So that ones that you might want to do for your reporting, or you want to build it back into a workflow. Like this is not specific to Delta or anything, but it's super simple and really powerful and allows your organization to be more productive, right? So from the data science aspect, a lot of them live within the silver layer of the data lake, right? Where you're kind of building these featureized data sets where you can augment it or kind of enrich it with different data sets around the business. But the real thing here is that, getting that kind of quality moving left to right. Bronze layer, yeah. So dumping ground for the data set. I mean, that's fine. Like, even if the data is messy or corrupted, as long as it's there and you're keeping it, you can worry about kind of cleaning it up later. You don't want to have to spend time and think about what data is going to be valuable for your organization, or you don't want to miss out. You say somebody saying like, hey, I needed this for my model, but you didn't have it, and so now you have to plan to ingest that type of data. Okay, silver, you can have different applied schemas. You can have it joined and augmented, and then gold is ready for consumption. So another thing is that because of this kind of like unified batch and streaming, it kind of allows like streams to move your data around the Delta Lake. So you have access to Spark, which gives you this low latency streaming, right? Where you do that kind of continuous processing, where you have like your cores on hold. But you can really think of it kind of in incremental computation, right? Where a query that you want to run continuously as new data arrives, right? And this is eliminating that management of schedules and jobs, and not having to worry about the kind of checkpoint states and so on. And so now from like the batch perspective, it also supports, your classic data manipulation, right? So your inserts and your updates and your merges, and this can be handled like on your on your Delta files, right? Either whether it be a stream or not, right? But it has the ability for those batch operations, and this can be important, if you have to, go back and do some kind of fixing of your data set, or merge in new data, or your schema has evolved somehow. So really, it's allowing you to choose the right tool for the job and seamlessly mix that kind of streaming and batch workflow. Yeah, so so talking about this, I mean, this kind of just highlights the same story here, but you can manage streams between your different tables, right? And in order to the streaming makes it really easy to restart that process and correct any errors, right? And it gives the end user a lot of functionality. So you can just really just like clear the table, create your checkpoint, and restart your stream. Okay, I think I'm going too slow here. So I'm going to, just, talk about data reliability, failed production jobs, lack of schema enforcement, lack of consistency. And then from the performance aspect, there are some things around like the too many files problem, right? Where you're dealing with a lot of IO that's taking more time than the processing, for example. Different partitioning and indexing. We still manage data sets with partitions, but it can cause issues if you've picked your partitions incorrectly, and you might end up with hot pockets of data depending on if it's like a time series data set, right? You might have some partitions that are very contain a lot of data and some not. And then caching. Okay, so how are we going to use Delta? Let's kind of dive down into, I guess, like the specific features around the reliability and performance. So first of all, just getting started, it makes it. This is Spark API, right? So this is the data frame API, but it shows you that you can write a Delta data set with just like one line change, right? And so if you're using Parquet files currently, there's no real downside of using Delta, really, or not that I've seen. And it's really easy to convert back and forth between the two. Obviously, if you don't have a Delta log, you won't have anything prior to your current conversion, but it's just really easy just to write to Delta using this API. So let's go about what does it look like on your data lake. So we're looking at like a specific table here, and you can see that we have our date partition, and then we have our file.parquet. But then in the table at the root level, there is this underscore Delta log, which is keeping track of these JSON files. And this allows you to store your metadata alongside your data set, and you're not having to have some kind of auxiliary database somewhere where you're pulling that metadata in, right? Where there may be limitations. So having the metadata associated directly with the file, I think, removes a lot of complexity when you're looking at your data lake structure. Okay, so you have your transaction log, table versions, your partition directories, and your data files. Sorry, I'm bad with the the slide animation type stuff. Okay, so what is actually in those table versions, and how are we going to reason about the current state of the table, right? So from the table's perspective, the table is just a result of the sum of all those actions, right? And those actions might be something like a changing changing the metadata, so the name, the schema, partitioning, and so on. Whether you add a file and you have optional statistics with it. So there are some defaults like file sizes and mins and maxes of specific columns that that get tracked, or maybe like removing a file. So your version is going to be like your current metadata and your list of files. Okay, so we spoke about how Delta is providing those ACID transactions and that atomicity, and the transaction log is going to be the single source of truth for your data set, and any reader will be able to come in and look at that Delta log and see those changes, which are stored as the atomic units called commits. I mean, for like the storage aspect, like there are different systems. Different systems do it in different ways. Like S3, I think, uses like the byte comparison to check, and HDFS and ADLS use a temporary file and an atomic rename. But let's take a look at an example of kind of what this looks like here. So we're having our initial load of our data set, like 0.json. And we're going to write two files. So 1.parquet, 2.parquet. And then in our subsequent action, our next commit, we're going to do a compaction process, right? Where we're going to remove those files, or compact them rather, and add back our 3.parquet. And so those are the, so in order to get the current state of the table, all we have to do is just look at these commits and figure out that, okay, well, after I've read these, now my data set is just like 3.parquet. Okay, so let's talk about serializability and the concept of mutual exclusion. So we need to agree on the order of changes when there are multiple writers, right? So this is important when you're dealing with actions like merge or different change data capture type processes. You want to be able to guarantee that serializability. So even though things are happening concurrently, you want to treat them as they are happening in a synchronous, ordered manner. So let's look at an example here. We're going to have two users, and they're both going to read, or user one rather, is going to read 0.json. User two is going to read 1.json. And so user two does some processing, makes a commit, registers that 2.json, and user one now sees that something is there, and then they will try to commit. And so they're either going to have to commit a 3.json, or if there's some kind of problem with their processing, they will get an error message, right? If there's some kind of mismatch between the changes that user two has made. And so this is an issue, right? I mean, it stops people from writing data set. Like, it's not really an issue when you're dealing with appends, right? But when you're dealing with changing the data sets, generally it's not an issue, because very rarely do you have people doing this kind of data manipulation concurrently, on the and where it affects one another, right? Most of the time you're just dealing with appends. So these conflicts, Delta is going to use something called optimistic concurrency, which determines how the writers should act when there are multiple writers, and when you're dealing with the same table. So let's kind of look at kind of what that was solved, or sorry, how this is solved. So pessimistic concurrency, is the case where you're going to have like a lot of writers, right? And you need to have that ability to lock the table. But but like I mentioned before, because it's relatively rare to have these concurrent writers, so we chose the optimistic concurrency. And so how that works is you record a start version, record the reads and the writes, attempt the commit, and then check to see what was changed in that commit, right? So that would be like that user 2 committing that 2.json. And then they either can try again later, or depending on the operation, if there was no problem, they would be able to write out like a 3.json. So, okay, so here, user 1 and user 2, we record the state, the start version, that's 0. Now they're going to do the read and write. User 1 is going to attempt to commit. Let's see here. Yeah, user 1 is going to attempt to commit. So user 2, he'll check to see if anything has changed. And if nothing has changed, then user 2 will be able to write out a 2.json. And if something did change and they were modifying the same data set, they would have to throw an error, and it just turns out to be a race condition at the end. Okay, so now let's talk about like the scale, right? The aspect of scale. How are we going to handle the massive amounts of metadata? So we're dealing with big data, a ton of files, tons of partitions, and not only that, but now we're creating all this metadata, right, in the form of JSON files, right? And so you don't want that metadata to be the thing that brings your system down. So we can use Spark kind of in a subsequent workflow, right? And what happens is that we can read in that data set and create different checkpoints along the way. And so by default, the number of commits is 10 before making a checkpoint. And so by doing this in 2 phases, oh, sorry, I think I missed a slide here. So, yeah, so by doing this in 2 phases, you can drastically reduce the amount of data that needs to be processed, right? Because you're just going to have to look at your checkpoint plus whatever the new commits are that is stored within your transaction log. I mean, and yeah, so this is definitely better than, having to continually hit some kind of metadata store, where you can run into bottlenecks. And yeah, it's just better for scale and dealing with that kind of incremental computation. So how do we compute that the delta state? I mean, we just have to read them in order, right? We have to read these 3 commits in order. And what Spark will do is it will take that and it will cache those commits or cache that state in memory. So when you're querying your Delta table, you can use this in-memory representation of your table to answer specific queries. So here we're going to do cached version 2. Okay, but so now we have this version 2, and we want to be able to update Delta state. So we're going to add a few more files here. So let's see. So here we're going to add five new files, giving us this version 7. And so you can call like the method list from, which reads the Delta log. And it's going to input all those new JSON files as well as the cache and play them just in a sequential order, right? And so if you're constantly querying your Delta table, you don't need to worry about state management. Instead, the cache just detects if there are any new writes. So here we're going to cache version 7. Okay. Yeah, I realized I should have maybe done like a demo because, I realized it's kind of, it gets kind of boring towards the end, kind of going through this stuff. But okay, so now we're writing some more commits, and like I mentioned here, 10 is the default before you do a certain checkpoint. So at 10 we have a checkpoint. So instead of reading kind of that cached metadata, we're just going to read the checkpoint and cache version 12, right? So that's going to be only the 2 commits, right? Which this makes it a lot easier and faster to update Delta state. Okay, so the aspect of time travel. So because we have all this metadata associated with our table now we can have this feature called time travel. And what's really nice about this is that it kind of just gives you a really simple SQL syntax to go back and load a specific version that you wanted to, if maybe there was some kind of corruption or maybe the upstream system went down, writing bad data, right? You can kind of revert back to an original version and load it with like different types of syntax here. Here it's like version as of, or you can use an @ symbol, or you can use like the data frame API to load it from a specific path. So that's really cool. And like I said before, mainly just for fixing mistakes, not necessarily for like versioning your data for modeling and stuff like that. And then, I mean, it can also do it by timestamp. Timestamp is a little trickier, right? Because you're dealing with timestamps relative to storage system modification times, right? And so when you're dealing with distributed systems, you can definitely have things like clock skew, and it does not guarantee this monotonically increasing timestamp, right? And so how to get around that, like behind the scenes, there's like a small adjustment of like 1 millisecond made. So in order to like query specific time, you can look at the latest version to that timestamp without going over in kind of like this Price is Right style. But for the end user, it doesn't really matter. Like you can look up by timestamp, and Delta behind the scenes is going to do that kind of performance optimization to find out where your data resides. Oh God. Okay, so let's go through data skipping. So now we're tracking each of these files. We can calculate these column statistics. The most common one is like the min max value on the columns, right? So like in SQL Server, I think it's called like column store index or Oracle zone maps, but you're essentially automatically tracking all these different statistics for your columns, which makes the query to essentially cut down on that IO time by skipping reading the data set, right? So here's a filter example where you can like filter by select star from table where the column is less than 5, right? And because the min and max is out of that range, so you're not going to have to actually load your data set, right? That is unnecessary for your query. And so this really is beneficial for the interactive queries, but then also, right, like if you have to go in and do the surgical removing, right, like the updates and deletes, it really kind of speeds up that process because you're not searching over your entire data set and you're leveraging these column statistics. Okay, and so delete, again, you can just have this really simple SQL syntax, right, where it's delete from my table where predicate. And this kind of highlights the simplicity of the API design, right? Where you have this syntax that's really common for people coming from the database background, right? And so yeah, so you can look at the statistics. Sorry, let me just skip ahead here. So yeah, so you use your predicate to filter to handle your data skipping. And you'll leverage your data skipping to figure out which ones match the predicate, and the delete operation uses the copy on write, right? So essentially, if you're deleting one row from a file, you can go in, you can find that file, load it, load that file, remove whatever what it is that you need to, and then write it back out as a new file. So that's the copy and write, and rewrites that file that matches the predicate. This can also be done. So this is actually one thing that pretty much drew me to Delta initially, and it was this merge simplicity, where you kind of have that simple SQL-like syntax, right? Where you can merge into on a specific condition, right? And then you can have these different operations like when matched, delete, for example, or like when matched, update, and then when not matched, we're going to insert, right? So we're like append the data set. And this uses the same trick, right? It uses the data skipping, so your partitioning levels, as well as your column statistics to figure out which files match the predicate. And it's going to ensure one-to-one mapping, and we're going to use that copy on write to only remove what we need to, make that change, write it back in. Okay, so there is an optimization built in, so you can when this kind of comes down to the tiny files problem, right? So if you have a lot of tiny files, you're dealing with that slow I/O times. So you want to make sure that your file is big enough that your processing time is going to be worth opening that file. So you can simply just run and optimize on your table, and it will automatically compact that data set into manageable files and specific blocks. Okay, and so with respect to data skipping, right? So like what happens when all of the column statistics are the same, right? And so now you're not getting the column statistics are no longer meaningful, right? And it doesn't allow you to skip any data. So there's something called Z ordering. And so this is like a multi-dimensional clustering algorithm. And it allows you to, so it's kind of like high level. I'm no expert in this, but it allows you to kind of map the data to a binary space, then interleave the bits. And this is going to be, so you have like your X's and Y's, and then it sorts it in this space, resulting in this kind of Z-Z pattern, where the data is now co-located. So if you're filtering on X equals 0, Y equals 0, it's going to be in the same file, whether you, as compared to if you just sorted on those two columns. Right. So what this is good for is when you are dealing with columns that you're going to filter on a lot, right? Or if it's something that you're specifically going to have to go in and do a lot of updates and deletes on. So it's really beneficial to do this kind of optimize my table and then Z order by specific columns. And you can, just like an example would be something like time, right? You can have month, day, or month's day, for example. I'm almost done here. So Ben, I know I'm kind of running out here, but just a few more slides. Okay, so let's talk about optimized writes. Okay, so here is like a particularly bad example, right? Where you have all these different events and split up across all these different executors, and they're going to have to write out to different partitions, right? And so we're going to have to write out like A, B, C, right? They're going to have to go to these different partitions. B looks okay, or sorry, executor 2 looks okay because it has 3 Bs on 1 C, for example. And so, this is that kind of that tiny files problem, right? Where you're kind of bottlenecked by I/O, and so you're not necessarily limited by the processing, right? It's mainly the storage layer, right? That's going to kind of decrease your overall performance due to latency, right? So how are we going to fix this? When you have to write out, essentially we're just going to do another shuffle at the end of the job to co-locate that data based on what partition it is supposed to go to, right? So now you can see that yes, shuffle operations are costly, but at the end of the day, on most cases, what I've seen, it reduces the time that it takes to actually run your data pipeline because you're avoiding that throttling problem, right? And so you can see we've done this shuffle, and now we have all these events lined up that kind of go to the specific partition. So yeah, you can so we're able to do things like automatically detect when data has been written to a delta table. And so you can have all your data streaming and processing, so you can have all your data processing, like your event data, and you can automatically detect when new data gets pulled into that stream without restarting it. And so that is beneficial because it kind of reduces any manual kind of checkpointing or start stops that you have to do. That could be very prone to errors. I kind of talked about this. Yeah, this is dynamic data skipping. So Z ordering with your data skipping. Okay, and so I just want to kind of summarize it here. So some of the Delta key features, really, ACID transaction is one. So we're kind of bringing the data warehouse capabilities to your data lake, right? Because you want to, enable the users. You want to make it make all your data usable, right? Your data has all this gravity that is sitting in these, cloud-based storage services. Right, you want to make sure that you're getting the best out of it. So some of those key features are the ACID transactions, scalable metadata handling, time travel, nice feature, fixing data sets, the open format, kind of preventing that lock-in, and making sure that you can run Delta on Databricks, for example, but you can run it in Synapse, you can run it on your local machine, whatever you want to do, right? So having that open format, I'd encourage you guys, even if you're dealing with CSV files, for example, you should try storing some data as Delta and see how you can do your processing, just for kicks. The unified batch and streaming, and then you have your schema enforcement, but also allowing the schema evolution as well. So it allows that flexibility to your data set, giving you that audit history where you're able to go back, you can track changes, you can make updates when necessary. Then you have access to that really common data manipulation operations that are relatively easy for any data savvy people to go in and do manipulations on the data lake. And then it's 100% compatible with the Apache Spark API. So anybody who's doing the big data processing workloads should definitely give Delta a shot. So that's all I have. And then I guess the last thing that I wanted to mention is that we are hiring. So we're hiring a solutions architect in Calgary, Alberta here. So I posted in the job opportunities. And so definitely reach out to me if you have any questions, either about Delta, Databricks in general, or if you want a referral for a job opportunity. And that's all I have. So I guess,
Chris, that was
questions here.
Awesome. I'm a little bit blown away. I love how, you really went through everything. Consider me sold. I'm going to be trying this out locally in some of our systems as well. So that was incredible. Yeah.
It kind of got a little bit. So I was telling Ben that I was doing this kind of prep last night, and I realized how boring it kind of got towards the end there. And I was just like, oh, okay, well,
I mean,
next time I'll
really,
do it or something.
I don't know. I guess it depends on your definition of boring. The nerds probably had eyes this big around. So, awesome. So we got a few questions. We'll take a few questions before shifting back to the lunch break. So first question. So what are some of the strategies from your experience for handling some of the schema drift in Delta Lake?
Yeah. So I think, like I mentioned in one of the slides, it has the that ability to both enforce the schema, but then also deal with that kind of that schema evolution. So it's literally just a flag that you can turn on and off and say, I want to. I forget what the flag is, but you can just say, yes, I want to allow my schema to merge. And I think, you know, if you're dealing with kind of like an appending type data set, it would just fill your data set with that column. With
and kind of related, I guess the question is, can you still time travel when the schema has changed for a given data lake table, especially I guess if like you're, you know, querying on changed schema columns, or for example?
Yeah, so the schema the schema change, that is just going to be again stored as a specific commit, and so you'll be able to revert back to a table that that doesn't have that evolution on it. But yeah, like I mentioned again, you know, I was definitely under the wrong impression when I heard the term time travel, right? Yes, it is data versioning, but really it's only a snapshot. If you're interested in kind of making longer term storage for your data set, or actually dealing with versioning, there are things called like there is a clone option available, or like a deep copy. So I encourage you guys to like look into that if you really want to say, I want to create like monthly snapshots or something, or hey, I'm doing some modeling, I need to create checkpoints.
Makes sense. I also remember from the beginning, early in the presentation, you were, you know, actually top of the slide right now, ACID transactions. You know, how ACID really is delta lakes. I know that there's a range from, you know, where like RDBMSs will be generally like fully ACID, NoSQL will be, you know, kind of eventually consistent. Where does delta lakes fit in that?
So I guess off the top of my head, I'm not sure about the level of ACID transactions. I didn't actually even know that. I figured it was either ACID or it wasn't. But I would just say I'd have to look into it. But you know, it does provide a lot of that atomicity, the consistency and isolation type things that you get from the ACID feature. I haven't really seen any awesome issues with that.
And I guess just like last bit of that question, and then we'll hand out. You know, what kind of trade-offs were there in the design of delta lakes for kind of like read optimized versus write optimized? Okay.
So I'm not sure. Yeah, I'd have to look into it. I know that, you know, like Databricks is still, it is an open source project, but Databricks is still kind of like really heavily behind a lot of the development on it. And there are like so many different performance things related to read write happening all the time, and new features consistently being added. So yeah, I encourage you guys to just go to the delta.io website, see some of the features available, and see how it can be incorporated into your workflow, either, you know, like I mentioned, locally or on a larger scale for your actual.
Cool. Well, thanks so much, Chris. I really enjoyed it. I'm sure everyone else did as well. And I'll take everyone back to the floor. We're actually on a lunch break now, so I think this Remo event will close in about 15 minutes, and then you'll have to move into the afternoon sessions. The afternoon sessions have a separate link. This is a restriction of the Remo platform itself. So just you can download the program on the right-hand side, and that has links to all of the, you know, future events, or however you navigated to this event, you'll be able to follow those links around. And yeah, feel free to reach out to Chris or myself in the floor if Chris is sticking around. So awesome, cool.
Yeah, I'll stick around.
Take care, you guys.
Yeah, please come chat. Okay.